Hey y'all, I'm going to walk you through how to find the initial conditions for an RLC circuit. We're asked to find dic dt of 0 plus for a parallel RLC circuit as shown. I went ahead and redrew the circuit and labeled the parts. And when you get an RLC circuit, it can be really confusing sometimes because there's a bunch of different things that they could ask for you to find. You could have the current through the resistor or the voltage across the resistor or current through or voltage across the inductor or the capacitor. So that's a lot of different variables, and each of those require two initial conditions because it's a second order circuit. And really the most effective way I've found to find the initial conditions, all of them, for an RLC is to fill out this table. So every time I come up with a problem like this, I literally write this out on a piece of paper, and I have the header as the voltage, derivative of the voltage, current, and derivative of the current at the time in question, which is almost always 0 plus. And you can find the voltage, you can find VL of 0 plus, VC of 0 plus, VR of 0 plus. Those can be totally different things, right? So you can have up to 12 initial values to solve for this circuit, which seems kind of daunting, but you kind of need to find all of them in order to solve the circuit, is what I found. If they're asking for something weird, like current through the capacitor as a function of time, there's no characteristic equation that directly gives you the current through the capacitor unless you have an integral, and it's a mess. I use Ohm's law to get from here to here on this table. I use KVL to go between rows, or KCL, and I differentiate to go between these two and these two. And you can also use Ohm's law to go between these two squares here. High level, what you're doing is you're filling out the table, you're plugging stuff in as soon as you know it, and you're using what you know about circuits to solve for everything one at a time, and it's not really that bad once you get going. Okay, so I've drawn the circuit here before the switch is closed. This is at T negative infinity or T0 minus. And we know that our inductor is a short, our capacitor is an open circuit, and taking this as ground, it looks like there's no voltage across the capacitor before the switch flips. And by extension, there's no current flowing through the inductor in this case. We know that the voltage across the capacitor can't change instantaneously, nor can the current through the inductor. So we can automatically put those two in our table, and we know that's going to be true even when we flip the switch, okay? I don't know what's going to happen to the voltage across the inductor when the switch flips. I don't know what's going to happen to the voltage across the capacitor or the current through the capacitor once the switch flips. But I know for sure that these two are going to stay the same, so you don't have to worry about those, right? So now we flip the switch. I've relabeled my parts, and we've got our circuit here. I've only found two of these. What am I going to do next? Well, just looking at this, the capacitor is in parallel with this inductor. So even though the switch is flipped, I can already see that this is all one node right here, and nodes share the same voltage. So by extension, that also has to be 0, right? And if this were a series RLC, then you would say the current would have to be the same. But that's not necessarily the case here, because this is a parallel. So the current could be something totally different. I don't know what that is, but I do know that the voltage is definitely 0, because it has to share the same voltage across the capacitor. Okay, what do you do next? Whenever you have 2 out of 3 of these in a column, do a KVL or KCL to get to the third one. That's the beautiful magic. You got 2 out of 3, I'm going to do a KVL. I say that the voltage across the resistor plus the voltage, the voltage across this is the same as the voltage across this, because they're in parallel. We just established that. I just call it VLC. That has to equal VS. And plugging in your values, you get, look, the voltage across the resistor is 3 volts right when that switch flips. Agreed? If we know the voltage across the resistor, what else do we know? We know its resistance, we know the voltage. That sounds a lot like Ohm's law. So we use Ohm's law, remember, to get between this one and this one. And doing that math, you get a current value. And I'm going kind of fast because you should know this stuff, but you can do the math on your own if you need to pause or whatever. I've got 2 out of 3. What do I do when I have 2 out of 3 in a column? I do KVL or KCL. I've drawn the arrows the exact same way they show in the diagram. So there's 1 coming in, 2 coming out. That means IR is IL plus IC, and I already know these two. So it's super easy to find IC at t equals 0. Okay, now we have all 6 of these. We're halfway there. How are we going to find the derivatives? Always start, when you start doing the derivatives, always start with your characteristic equations, okay? Note that this is true only of IC, not IO. This is true only of VL, not necessarily VC. And you can do that math at home or whatever. Look at that. Even though the switch flips and there's no voltage across the capacitor at t equals 0 plus, there's 4,709 volts per second is the slope of that graph. So it's actually changing pretty quickly, even though it's still at 0 at that moment. But this is definitely 0. What now? Remember when we said that the voltage across the capacitor is also the voltage across the inductor? That's also true of the derivatives. So we already know 2 out of 3 of these. What do you do when you know 2 out of 3? I'm going to do a KVL. I say, look, this is the same KVL we had before, okay? But I'm going to differentiate it because it should hold true even when I differentiate it. And since we know that in this case, our voltage source is constant, its derivative will be 0, such that dVR dt is simply negative dVLC dt. Okay, I hope you can see that. We're just characteristic equations, KVL, and remember, if this were in series, then you'd say that they'd have the same di dt. Well, they always have something in common. All these RLC circuits, they have something in common after you have the characteristics. Ohm's law. What happens when you differentiate it, right? We said this Ohm's law was the link between these two, and you can differentiate between these two. So when you differentiate Ohm's law, you get the link between these two squares here. And I just pulled the 1 over R out in front to make it look a little cleaner. But when you do that math, you get dr dt is negative 673 milliamps per second. And then your last thing, you've got 2 out of 3. So I do a KCL. I define it the same way. Remember that this is 0. This is negative 673. So there's your final answer. You can apply this same reasoning to series or parallel. I use the same method either way. But what you got to remember is you take Ohm's law to go between these two, or between these two if you differentiate it. This is differentiation, this is differentiation. KVL, KCL will get you up and down between the rows, right? And now we found 12 initial values, so you can solve for any of the 6 functions of time that you might be asked to find in an RLC circuit on an exam, or I guess in real life. I hope that was helpful. The end.